Thank you everyone for joining today's webinar. So my name is Ryan Ahola. I'm a geospatial expert with Natural Resources Canada, which is a federal department of the Canadian federal government. So I'm based in Ottawa, Canada. I am one of the co-chairs of what's called the Climate Resilience Domain Working Group as part of the Open Geospatial Consortium, which is facilitating this webinar. So just a bit of background about the Open Geospatial Consortium and OGC and why we're here. OGC is formally a standards development organization, so it focuses on the creation of open geospatial standards. So you've likely used a lot of OGC standards inadvertently. You may not have known that you're using them, but they're used quite widely for helping users and machines like computers find, access, and share geospatial information consistently. OGC does a lot of work to engage with its community to ensure that its standards meet practical needs. So it does that primarily through this concept of domain working groups. So there are many different working groups within the consortium that focus on a particular domain area to understand interoperability challenges and aim to identify solutions that can improve the standards that OGC creates. So I'm one of the co-chairs of what's called the Climate Resilience Domain Working Group. So we work on the climate resilience domain to try to improve standardization in that effort. So in that context, we are working with the Focal project to host a series of webinars, with the first one being today. So Focal is a European project that is working to make climate data more actionable by integrating tools like artificial intelligence, high performance computing, and Earth observation data. So for today's webinar, we're pleased to have Dr. Guy Brasseur from the Max Planck Society for the Advancement of Science. So Dr. Brasseur is going to provide a general introduction about the methodology behind global climate models. So this will include examples of the fundamental nonlinear equations that are used to calculate things like the flow of air in the atmosphere, the flow of water in the ocean, as well as related temperatures and humidity. He is also going to provide information about the methods used to solve these types of equations, and will refer to the use of empirical parameterizations to describe processes that can't be explicitly calculated. Professor Brasseur will give the presentation, and then following that, we will have a question and answer session. So please feel free to take note of any questions that you have, and we'll get to those at the end of the presentation. So with that, I will pass the floor to Professor Brasseur to begin your presentation. So please go ahead.
Okay, thank you very much for your nice introduction. So I'm Guy Brasseur. I'm at the Max Planck Institute for Meteorology in Hamburg, which is part of the Max Planck Society. I'm also with the Focal project. And so what I would like to do today is really to give you a kind of a feeling of what a climate model is. I'm not going to go too much in technical details, but I would like to give you the impression that those models are really trying to reproduce basically the state of the planet today and have some capability in projecting how our climate will be changing in the future. So if we want to understand in a very simple way what climate is and how climate works, we have to look at basically the radiative transfer that occurs in the atmosphere. We have the incoming solar radiation, about on the average 340 watts per square meter. Some of the light is, of course, reflected to space, about a third. The other part is absorbed by the Earth system. That's the solar part of the balance. But then the Earth itself is emitting infrared radiation, and a large fraction of this radiation is absorbed by gases, in particular in the atmosphere, CO2, methane, nitrous oxide, and so on, so the greenhouse gases. Some of the radiative or energy that is absorbed by these gases is re-emitted partly back to space and partly back down to the surface. And so all the system in principle is in energy balance over time. But of course, if we change some of it, for example, if we change the amount of greenhouse gases in the atmosphere, or if we put some particles in the atmosphere, we get a certain imbalance. And today we believe that there is an imbalance, and that imbalance leads to some climate change with generally an increase in mean temperature of the planet. And so this is summarized here. We derive basically the energy balance by looking at how much is absorbed by the Earth system, how much is emitted by the Earth system to space, how much energy is trapped in the Earth system, and how this net effect is changing with time. Of course, it is a simple calculation to show you on the slide, but in reality, of course, there are a lot of processes that need to be taken into account, and I'll show some of that a bit later. Of course, what we know is that the greenhouse gases concentration in the atmosphere is changing, in particular CO2. And you see here basically the amount of CO2 as a function of time that was measured at Mauna Loa, a site that is removed from a lot of the industrial sources. So it gives you a bit of a picture of how the northern atmosphere is responding. You see the increase over time since 1958 until present. And on the right panel, you see how the temperature has been changing, in this case here since 1940 roughly, with an increase in temperature compared to the pre-industrial period, which is today close to 1.5 degrees. Now, as I said, as we look into that, greenhouse gases are important, but there are a lot of other processes that need to be taken into account. Some are forcing the system, but some are part of the response of the system, and some of them introduce some feedbacks in the system so that at the end, the representation of the climate system is complex. You see here essentially some of those processes, and they include, of course, atmospheric composition, greenhouse gases, aerosol, as I mentioned, but also the whole water cycle, which is changing and, for example, is connected to the formation of clouds, to the presence of precipitation. We have exchanges, of course, with the surface that need to be taken into account, exchanges of energy, exchanges of carbon, exchanges of nitrogen. And we have natural perturbation, like volcanic eruptions, for example. On top of that, we have human contribution to the changes at the surface, and all those processes that are very, very briefly mentioned need to be taken into account in climate models, because they're part of either forcing or response function. For example, you see here the sea ice. The sea ice is reflecting part of the solar radiation, but is also changing because temperature and therefore climate is changing. So another complication is that we need to deal with essentially different timescales that are occurring. You see here a graph that highlights timescales from, let's say, days to decades. Climate is, of course, considered as a long-term response of the system. But of course, it is the result of a lot of processes that occur at much smaller timescale. And so today, dealing with, for example, weather forecasts, sub-seasonal to decadal prediction, and long-term projection cannot be considered as separate tasks. They have to be taken into account. And you see, for example, here listed a number of processes that are basically timescale dependent and need to be taken into account because they all interact strongly in the Earth system. So in order to represent this, we are using numerical models. So what is a model? Well, it's an idealized representation. It's maybe an abstraction of an object, the Earth in our case, And our purpose is to demonstrate the most relevant or maybe selected aspect of this object and to make the object accessible to our studies. That's a very general definition. But you can also say that it's a structure, formalized structure used to account for an ensemble of phenomena between which certain relation exists, and this is also a good way, theoretical way of describing what happens in the Earth system. And so it's some kind of prototype, it's an image, it's an analog, and it is very important, an object that is isolated, that we can technically manipulate and that we can use to communicate to society what is happening. And so essentially, when we look at climate model, considering to be a mathematical representation of the chemical system, which is based, of course, on the physical, biological, chemical principle that those disciplines have brought to our knowledge, and that are translated in equation. In fact, we have to look at different parts. We have, first of all, the action of developing those models based on those principles, using perhaps equations that are representing those or simulating those principles, trying to resolve those equations and maybe also adding some approximation, some parameterization, very much driven, controlled, managed by observations. Then we have the models, and the models needs to be forced by some essentially actions. We see that the sun, for example, is a forcing. The humans eventually are also action, even though sometimes they include it in the model. So we have this external forcing based to a large extent to observation. We get results, and of course, these results need to be validated, evaluated, and perhaps used then as results that need to be analyzed by the scientific community, but also then, after the analysis is completed, communicate to the people who need the information. Of course, a climate model, as I said, needs to capture a lot of the different processes that I mentioned. And in fact, you can characterize them by two kinds of processes. You have the physical processes, and so we're talking about the physical climate system. And on the other hand, we have the biogeochemical system. In yellow, the physical climate system is in blue. And we have the human system also that needs to be connected. And you see here, you get a certain feeling of all the interaction that exists between these, including the forcing that I mentioned. And in particular, you see on the left, the natural forcing, the sun, volcanoes, another one. On the right, you see what I would call the human forcing, but it's not just forcing, it's also the impact on the human system, so that we need to interact, basically, the human system with the hardcore physical and biogeochemical system. This is why, basically, the history of model development has changed very much over time. In the 60s, we had essentially atmospheric model, and we found out that they needed to be coupled to the ocean. But as we did that in the 70s and 80s, we said, well, we really need not only to look at a coupling, but we need to really build integrated models that couple ocean, atmosphere, and in fact, also include the sea ice. Then we found out that atmosphere, land vegetation, ocean was not enough. We had to add some processes, such as, for example, introducing the biogeochemical cycle, and in particular the carbon cycle, introduce also particles in the atmosphere, came out of volcanoes or human activities, sulfate, aerosols, dust, different type of particle in the atmosphere. Then in the last years, we made also sure that the vegetation which interact closely with the atmosphere is interactive in these models, that the biogeochemical cycle are fully represented. And in the last years, a lot of work has been done on better representing in these models the sea ice. So if we started with the atmosphere as an example, we have, of course, to deal with the fundamental law of physics, and in particular with the law of motions that Newton established, which I will not repeat here. But this leads us to basically equations. Equations, which are they? Well, first of all, you have the momentum law, the conservation of momentum, where basically you express the acceleration of the winds. If we deal with the atmosphere, if it was the ocean, it would be the flow of water, but focusing now on the atmosphere, which in this case, in the atmosphere, depends on the number of forces, gradient, pressure gradient, gravitational force, friction, and also if we representing the winds in a framework on which we live, the Earth that is in rotation, we have to deal with the Coriolis forces. We have to add, of course, a continuity equation, mainly an equation that expresses the conservation of mass. And of course, it is also a function of the wind velocity in particular. We have to deal with the conservation of species, in particular water vapor, water mass, and of course, the changes depends on transport also, but also source and sinks of moisture, in other words, evaporation, condensation, and so on. And then we add the first law of thermodynamics that describe the changes or the conservation of energy, and finally the equation of state that relates pressure, density, and temperature. So these are equations, and in particular in the momentum equation, you'll see nonlinear terms, so that the equation is not necessarily pretty easy to solve. But of course, how do we solve this equation? There are different ways. Very often we use finite difference. We approximate the derivative by finite difference, so that basically we convert a differential equation into algebraic equations, and we do this discretization essentially in 3 dimensions. This is one of the approach. There are other ways by which you can address this. I'm not going to get into detail, but in reality, what we have to do is to replace the continuous medium, let's say the air in the atmosphere, the water in the ocean, by a grid that basically help us applying the approximation to the differential equation into a simpler system, but we will look for the solution of these equations. In other words, we will calculate temperature, pressure, wind component on the grid that is shown here, for example, on the nodes or in each of the small elements that are here. And you see here just a picture of this grid. The distance between nodes is called the resolution of the model. And of course, we always hope to have the highest possible resolution, but the higher the resolution is, the more expensive the resolution is. And this is why, in a way, climate model requires supercomputers that are very, very efficient. So there are different grids that have been used. The most classic grid is a grid where the lines are latitude and longitude. This grid, of course, is easy to understand and to remember, but it has one disagreement, or the problem, which is that all the meridian converge in the pole, and at the pole then we have difficulty of finding an equation, or a solution, so that other grids have been used and are being used in different models. So when the equations are solved, we find maps, if it's a global model in particular. You see here, for example, some of the solutions that are probably provided by a model, where you see the pressure field. And of course, the pressure field is characterized by a number of features. For example, you see on each part of the equator, high pressure cells. You see at higher latitude, for example, in the northern hemisphere, you see quite a bit of low pressure cell, and you see the winds then circulating around these pressure cells and providing us with a kind of a mean state of the atmosphere. This is a case for January, and of course, we have the model providing such field for every month, and of course, we can therefore look at the seasonal variation of the dynamic, the atmospheric dynamics, and how things evolve on the average, but also what is the variability associated with those fields, which is basically what tells you what the weather is. And this is what basically is the most important information probably for people who are affected by meteorology and by the climate change. So the model resolution, I just mentioned what it is. Typical resolution for global models today has been for a long time now, 100 kilometers, moving to 50 kilometers. And of course, the goal is to go to much higher resolution as we find new ways to speed up the resolution of the model. Could be more powerful computers, but could be also other approaches, numerical approaches, maybe AI involved, etc. But at the moment, in fact, the goal now of the community is to go to about a kilometer resolution, not immediately, maybe 5 kilometers, 10 kilometers, then we'll go to 3 to 1 kilometers. That's kind of the goal to do. And a lot of people are thinking how to do this. But at the moment, with relatively large grid or semi-large grid, there are a number of processes that we do not capture inside each of the cells. And these are called the small-scale processes, which are important to consider because they might influence the larger scale, the one that is resolvable. For example, clouds, cyclones, maybe even a part of hurricanes might not be well represented in low resolution model, and so they are parameterized. So inside the grid, we have subgrid processes that you see represented here. Here are some examples. First of all, the dynamics of the boundary layer is very much affected by small-scale dynamical processes, by turbulence, for example. The formation of clouds, you see there, for example, a convective cloud, very difficult to represent with a grid of 50 kilometers. You see also the relation between the atmosphere and the surface. You see the microphysics and also the radiative transfer that is, of course, occurring with processes that are not resolved by medium or low resolution model. So parametrization accounts for the large-scale influence of processes not included explicitly. And of course, in addition to that, to make the model work, we need input from observation and perhaps sometimes of other model studies like boundary conditions. If you work on a regional domain, you need boundary conditions that are provided by a global model. You have also to know the external forcing to drive basically your equations. I'm going to pass that. And of course, today, large computers are used to run the models and simulate for periods that have to be much longer than the one that are used for weather forecast, because here now we're running over a long time. By the way, these models are usually run as ensemble because the parameters that are forcing the system are not necessarily very well known. because there is chaotic behavior in the dynamics of the atmosphere, for example, so that we run the model with different initial conditions or slightly different conditions to see basically the spread of the simulation or the results of the simulation. And basically, when you see a scenario very often, it is the average of, for example, the temperature change based on a number of model runs, model simulation, an ensemble. We just calculate the mean and we provide this. So just to show you very briefly the kind of results you get for a model that attempts to reproduce the current climate. You see here the annual mean temperature surface, with, of course, warmer value in the tropical region, colder value at the pole. But it also shows you, for example, the multi-model mean bias that is calculated. Also, people try to derive kind of an absolute error or some inconsistency between models and observations. This is now the annual mean precipitation rate, which is probably more difficult to calculate when you look at different models or an ensemble of models. You have more variability because, in particular, in the tropics, the calculation is basically linked on very small-scale processes. Trying to get precipitation in a better way is probably more complicated since many of the processes are small scale. So I just showed you some of those calculation of the general circulation of the atmosphere. You now see two seasons. And of course, once you go to the ocean, you get also, of course, results of that nature that shows you the flow of water. You see the current, both at the surface, the deep ocean current. You also needs to account for the interaction on the land, with the land, between the land and the atmosphere, so that now people include dynamical vegetation model. And here, what kind of basically processes you have to deal with, interactions you have to deal with, certainly interaction with the energy, with the hydrology, and with the biogeochemical cycle. So it is a very, very important aspect of the climate models today. The models also include a sea ice model or component. And of course, these needs to be basically conceptually divided between the thermodynamics aspect, basically the growth of ice, the decay of ice with the climate situation, but also the dynamical aspect of the ice sheet. And this is a topic which received a lot of attention, has received a lot of attention over the last year. So now that we have reproduced with some degree of success the current climate, it's also important that we look at what will happen in the future. That depends to a large extent to how much CO2 or greenhouse gases will be injected into the atmosphere. And so we don't know what's going to happen, and therefore we rely on different scenarios. And here are three scenarios. They're a bit old. The first one in red, RCP 8.5, is roughly representing business as usual, so that if nothing was done. And the other ones assume that some action is taken to reduce emission, and the RCP 2.6 is kind of the wished scenario, so that we do not go over 2 degrees warming of the planet. And so I don't know if I will be able to make this work, but I think so. You see here basically the results of a model. This is the Max Planck model for two scenarios. On the right is the business as usual, if you want, RCP 8.5. On the left is kind of a lot of action taken to reduce the emission, and it's called RCP 2.6. And you see now over time, we're already in 2085, you see that basically we are expecting, based on those two scenarios, very different changes. These are basically 10 years running ensemble mean. So you see, basically, I was talking about ensemble earlier, and you see basically that those two scenarios provide very, very different solution, very, very different climate, and very, very strong changes or differences in changes for the population. You see here basically different scenarios that are used, and those are global, of course, but they also are very important for people who design policies. This is the situation in 2010 for, basically an Earth where the mean temperature would change from 1.4 to 4.7 degrees, 5 very different planets. Now, these are global results, but of course, people are very interested in regional results, higher resolution, regional, in order to be deriving impacts on water, food, energy, ecosystem, biodiversity, coastal area, tourism. Now that we move from basically the physics or the biogeochemistry associated with climate, and we move into essentially what people want to know, we need to get much higher resolution data, and therefore we try to downscale the results in the region that is of interest. And to do that, we're coupling or we embedding, in effect, regional climate model into the global climate model. And we do that basically, essentially by running the regional climate model, but we have a input in the boundary conditions of the regional model and a buffer zone to do a transition between those two models. And you see here, just to show you different results. This is the temperature, I think, in Spain and the precipitation in Spain. On the left would be the result that you would expect from a general circulation model. On the right is the result that you would expect from a regional climate model. And the observation is on the right, and you see that there are much more information once you start going to much higher resolution, using very often regional climate models. But of course now AI will be used also to do these kind of things. So downscaling basically today goes from global to the city block. People want to know what happened at the scale where they live. You start with the global model. Here again, RCP 2.6, RCP 8.5. You go to the regional scale, you go to the urban scale, and you go to the city block scale. And so this is kind of a lot of interest in those downscaling at the moment. Let me finish by just indicating that essentially, as we want a resilient society, we start to think much more into a global perspective, Earth system perspective, global or regional, but Earth system perspective that takes everything into account. I don't have much time to talk about it, but we need to understand the Earth system component and their interaction. We need to understand the interactions between scale. We need to understand the interaction between different external forcing. And so the research today from Earth system scientists is really to look at those interactions. And now, if you have time, you look a little more in detail. But if you talk about the, say, Earth system component interactions, you can see exactly as I said, land atmosphere, biosphere atmosphere, ocean atmosphere, solar Earth system, human system Earth system. If you look at the interaction between scale, we start to talk about points like tropical convection or ocean variability, weather, extreme weather that are occurring. So this is a bit of a highlight now of the scientific community to understand those. But of course, people also realize that those system needs to deal with the different scales and the interactions between scales. We need to deal today with wildfires. We have to deal with urbanization. and a number of processes that humans are introducing: agriculture, understanding the land, provide how much water is provided, for example, in some region. And so we need to do today to establish the priority for advancing Earth system predictability. And you can see that they are based essentially on connecting observations, data assimilations, modeling, and today AI and machine learning. You see here on this graph a number of topics that are the basis really for what we call today convergent research or Earth system science in our field, and the need to look at all these processes. But at the end, we need to bring them together so that they help leading to a resilience community. Okay, that's what I wanted to tell you in a very fast and perhaps not very deep way, but it gives you a feeling of how the field has been evolving in the last time and how important it is to continue to work in this issue to get better information for society. Thank you.
Okay, excellent. Well, thank you very much, Professor Brasseur, for that excellent presentation. So we certainly have time for some questions. So I would invite anyone in the audience to, if you want to ask a question verbally, go ahead and raise your hand, and we can have you ask it. You're also welcome to post questions in the chat, and we can ask them that way. So does anyone have any questions? Yeah, go ahead, Dean.
Yeah, thanks for that great overview. It's a pretty comprehensive and ambitious description of the whole climate modeling field, so very much appreciate that. It sounds like towards the end, one of the big challenges is how do we do downscaling, not just to the regional, but to the local level, and figure out exactly what the impacts are. I mean, one of the challenges, even with getting buy-in on climate action, is that people sort of have a hard time thinking globally, and they relate more locally. So I was just curious, how does the modeling when you're doing modeling at the local level, how does that modeling differ from the regional and global scales? And what are the differences in the type of data you require locally?
Yeah, so when we use, let's say, coarse models, it's a bit what I've been discussing. And of course, these models can be, you can just increase the resolution, particularly if you have a regional model, you start to go to, let's say, 1 kilometer resolution, but that's not enough. The difficulty of going higher is that you enter in a non-hydrostatic limit, so that your equations need to be taken and representing some processes that are usually not represented in traditional climate models. So people tend to do a number of things. For example, you can use large dissimulation models. It's called LES. So these models will go to maybe 1 meter resolution and solve the equation, but these models are pretty expensive to run. And also, essentially, because of the chaotic nature of the system, you know that if you walk in the street, the weather might be about the same, but the wind is changing all the time, and it's chaotic. So you have to run those large dissimulation model in a way that you can then get average information or information about, let's say, the mean and the variance and so on. So this is one approach, but it's not a doable approach for many reasons. And one of them is that it's expensive. It's just expensive. And so usually you cannot even cover a whole city to do that. It's just too expensive. You need also information about the detail of the city, the buildings and all this, if you do it over a city. So there is a tendency to go away from this approach, which a few people have been using to learn about it. But if you really want to go into a system where you provide information to people, I think the way to go now is to go to artificial intelligence and that's the way to go. Now, people are starting to do that. So I'm not going to say much more than that, because you have specialists who are kind of trying to look into that. But this would provide ways by which, in a relatively inexpensive way, you could provide to the manager of the cities, if you talk about a city, some information. You need, of course, in both cases, also in the model, you need data for different reasons. First of all, you need data about the geographic environment that you have, which is, if it's in a city, the buildings, the street, the emissions that are taking place. I mean, you deal with all of that. If you deal with AI, of course, you need to start defining what kind of input you need to your system to drive your AI system, and people try to look what are the dominant factor that will affect what you're looking for, which is usually temperature, precipitation, and so on. But I think that's a very open situation at the moment.
Mm-hmm. Yeah, obviously you need things like the surface type and albedo and all that sort of thing. Yeah. I mean, I know there's another question in the chat,
presence of trees and so on.
Evapotranspiration and all that.
And that's exactly what Focal is doing, by the way.
Right. Excellent. So maybe just, I don't know if there's any, I mean, it might be out of scope of this talk, but if you had a resource that discussed something about AI, because a lot of AI, when people talk about AI or LLM, which are not really conducive to climate modeling, there are geospatial foundation models, which are more based around Earth observation. What type of AI model, are there AI models that are geared for spatial temporal field analysis that represents the Earth atmosphere?
I'm not the right person to answer that question, because I'm not really doing AI myself yet, but of course I'm following quite a bit what's happening. But this is probably a question for the people who are trying now different methods to deal with the climate system. In fact, also the air quality people are thinking of using those methods to predict air quality, because the chemistry model are also very expensive to run. And right. So I think you should probably talk to the people who are trying to establish those kind of approaches.
Atmosphere chemistry. Okay, thank you. Yeah, I don't know, Ryan, you want to read out the question from the chat there?
Yeah, no, thanks, Dean. So yeah, we do have a question in the chat, which says, so how can climate model outputs via downscaling, potentially downscaling, be used in real world carbon or green projects in developing nations where I guess financing and technology can be a limitation?
How can they be used? Is that?
Yes.
Okay, this is, of course, 10 years ago, people started to think about that. You had, very interesting climate models that made the scientists very happy. But when we were talking about the users, they said, well, we cannot do anything with that. That's not what we need. And so the first attempt has been to create climate services. Climate services has been established in several countries, with the first task to really understand, for the scientists in particular, what were the needs of the people who needed data. You know, if you talk to the mayor of a town, or if you talk to a farmer, or if you talk to the head of a company, they told you that they are very concerned about climate change, and then we wanted to know what you need. You know, I was running a climate service like this in Hamburg in Germany, and so we got reactions that were a bit unexpected to us. We found out, first of all, that the people who really wanted information were the people who made long-term investment. You know, like, for example, the banks. So we didn't expect that the banks were very interested in getting informations. Or, for example, the people who run the train system, because they once they do something, it lasts a long time. So we started to build information sheets, for example, for these people. We were kind of surprised that some organizations felt that they didn't need information when I think they did. For example, farmers were saying, well, you know, what is climate change for us? It's just 1 or 2 degrees warmer, but we have years that are 10 degrees warmer and years that are 10 degrees colder. We know how to deal with that. So there was a lot of information that was needed between, or communication that was needed between the climate community and the society, the economy, and so on. But of course, we were not in a good situation 10 years ago because we couldn't really provide the information they needed. And so I think with the emergence of new techniques to downscale and to bring information in a different way, exactly what Focal is trying to do, now the information that we can provide is much more fine in terms of scale, and also much more understandable. So people do not need to know the mean temperature and the mean precipitation. They need to know how often they will have an extreme event. So they think in terms of risks. And so today, I think the information needs to come in the form of risk, in the form of indices, in the form that they can really use in order to build mitigation policy, adaptation policy. Adaptation in particular is the kind of thing that we have to help them successfully implementing.
Great, thank you. I think Eva has a question.
Okay, hi. So thank you first, Guy, for this really excellent overview and the insights. It's excellent as always. I wanted to make a short comment, Dean, on the discussion before on the downscaling. As I'm also part of the Focal team, and we have partners there who are actually looking into these kind of methods that Guy was referring to. I'm not an expert myself. I had a look. Unfortunately, today we don't have anyone from that group here in the call, but definitely we are going to plan in this webinar that we are organizing for Focal. We are also going to look into that topic specifically. So I think there will be a whole webinar just concentrating on that topic, because that is of course one of the strategies we are looking to how to make climate data more accessible on the local level, and this is AI methods, not only, but yeah, that is one of our focus in Focal. So yeah, thank you for that question. I hope we can provide you with more in-depth research on that in one of our other webinars. Yeah.
Great. No, thanks, Eva. Yeah, I guess that's an encouragement to attend the future talks that are coming up. I was just going to make a very quick comment on the past one. I suppose, Guy, you can use RCM, regional climate model outputs, as forcing values for local high resolution impact models like flood modeling, right?
Yeah, that's exactly what's done. Yeah.
Okay, thank you.
We probably have time for one more question. Oh, here we go. So a question in the chat, from your experience, what are some key barriers preventing climate model outputs from being effectively used in policy and planning decisions?
Well, I think it's because the models do not provide the kind of variables that people need to use, and they don't know how to use it. And so this translation of, what is a physical variable into a variable that can be used and that is more based on risks and on something that is wished by the people. Well, this translation is really happening at the moment. So I think that in 2 or 3 years, maybe 5 years, this problem will not be as acute anymore. The mayor of a city or the farmer will not look at the scenarios anymore. I mean, we have been providing scenarios, and the scenario tells you that the temperature will increase between 3 and 7 degrees. So if you're the mayor, what do you do with that? Nothing. I remember one day in Germany, I had a conversation with a minister president in Dresden of the state there. And so he asked me, could you tell me what the temperature in Dresden will be in 2040, something like that? I said, well, it will be something between 2 and 5 degrees, depending on the scenarios. He said, yes, but I cannot do anything with that, because here's the thing. If it's 2 degrees, my economist will build my strategic plan for the development of my state in a certain way. If it's 7 degrees or whatever, 5 degrees, it will be a completely different economic model for the next years. So he said, when you go to the OECD and you say, what's going to be the rate of inflation in the next year? If they told me, we don't know, depends on this, and this, they just give me a number, and we put this number in the system. And if this number is wrong, it doesn't really matter, as long as we put a number in the system and we can calculate. If the number appears to be wrong, we'll change it in 6 months. So basically, they need a certain type of information that is scaled to the way they operate and not the scientific community operate. And so it's very difficult for the scientists to think in those terms. And so, again, this is why, a project like Focal and the others in the world that do the same thing, I guess, are trying really to work with the stakeholders and say, what would you like to have as information? And then, we have the base information from the climate model, but we have to translate that into some data that they need.
Okay, perfect. No, thank you. And maybe I'll ask one last question. So since we're hosting this webinar as like a function of the Open Geospatial Consortium, I'd like to ask a question about interoperability. And what do you think I guess the state of interoperability in this context of climate modeling is? How difficult is it to get the information that you need into the climate models or to share the information outside of it? Because that information would be really helpful for OGC as we work to design standards that can be used for climate modeling.
Well, first of all, the big global models are run in different countries by different groups. They required big computers, supercomputers. They required big teams, a lot of people working on them, constantly improving them. But the community has organized itself to make sure that all these efforts came together into a model comparison exercise, and so on. All that is related to IPCC, to the Intergovernmental Panel on Climate Change. So there are groups that exist, CMIP and so on, where the people run the same scenarios, the same condition as much as possible, but of course they get different results because their models are different. They try to understand the difference and why. So do not expect the mayor of a city or the farmer or the industry person to use those models and try to operate them. It's just too complex, too costly. This is again one of the objectives of projects that try to base on information from these models to provide not only data for direct use by stakeholders, but also a platform that they can use to run themselves different conditions, different scenario, using AI in particular. And so there is we're just talking, for example, now in Africa. Okay, they need to get information in Africa. They cannot run models. They don't have the capability. They don't have the community. They don't have the supercomputer. But they can access the world of climate models through the platform that are being developed now and that can be used in a few minutes on a PC, knowing, of course, that they have the data, that they can access the data, their big database that are needed to provide the base information that you need. So all this effort is going on, and I think you'll see a lot of progress in that direction in the next years.
Okay,
but
excellent.
maybe just a quick follow-up to Ryan's question. And maybe, again, from an OGC perspective, clearly the global community, IPCC, you're constantly sharing model and comparing model results. A lot of that is like, for example, using the climate profiles for things like NetCDF or ZAR. But those kind of data cubes are kind of difficult for the average planner at the urban level to work with. So are there any sort of gaps in the open standards? And I'm not just thinking about human clients, but also AI clients, because I'm not sure how well most AI are tuned to consuming data cubes, right? Whereas AI can work with GeoJSON just fine. So
maybe Eva should respond to that.
So I'm just wondering if
I don't think there are really gaps. Maybe, I don't know, maybe depending where you want to apply your prediction or your study, it's clear that, I mean, we're talking about Africa. There are probably not very many data there that, for example, to train your system. So you might want to train your system with models, but the models are not reality, right? And so in this case, for climate, the training, I think, is a big issue. It's not so much of an issue for the weather, because the weather, you have a lot of previous situations that are similar that you can use to train your system. But in the case of climate, you don't have necessarily an example of an Earth that was 5 degrees warmer and data that characterize the situation under those circumstances. So the way to train your system is by using models, that data from the models, for example.
But you can also train with satellite data or do backcasting.
Not for the future.
Yeah.
Yeah, of course you can use satellite data, but satellite data, we do that. We do that. But of course, it doesn't mean that the satellite sees everything you need to put in your system. But for climate, it's more complicated because we don't have a satellite that is operating in 2050 at the moment.
Yeah.
Okay, perfect. So I think we're basically out of time. So thank you everyone for asking your questions. Thank you, Professor Brasseur, for your excellent presentation and your responses. So we do have another focal project webinar coming up this week. So on Thursday at the same time as today's meeting, So there'll be a presentation from Dr. Diana Rechild, who's going to talk more about the availability of climate data and how that can be integrated into local climate change assessments and other types of workflows. So you're certainly welcomed and encouraged to join that presentation that's coming up on Thursday. Oh, and Muthu's put a link to the webinar in the chat for that, so you're able to have the information to connect. Yeah, so hopefully we'll see some of you on Thursday.
So Diana, by the way, Diana is in the climate service. So she is really at the edge or the connection between basically the science that I'm kind of representing through a Max Planck system and society, which is using data. And so she's extremely knowledgeable in these aspects. So it's a good idea to have her.
Okay, excellent. Yeah, so we look forward to her presentation. Yeah, and until then, thank you everyone for attending and enjoy the rest of your day. Thank you.
Okay.
Thanks a lot. Goodbye.
Yeah, thanks. Thanks everybody.
Bye-bye.
Thanks, Keith.
Thank you. Bye-bye.